one more exam, practice exam on Moodle, because exam 2 clearly just covered chapter 5, the one that I have already there. So I added practice exam 3 from last semester, and it covers chapter 7 and some other chapters that most probably you wouldn't be able to solve them. So today I'm going to send you an email what exactly in the practice exam, what questions in exam 3 you can solve. So let's just sum up what we were talking about the last time. Or on Wednesday, we said that there are 3 quantum numbers. One of them is n, which is the principal quantum number. It represents the shell, or that means how close are we to the nucleus, the energy of the shell. And the second quantum number is the angular quantum number, where L depends on n. It can take any value from 0 to 1, 2, 3 until we get to n minus 1, where L equals 0 represents an S subshell, N equal 1 that represents a P subshell, N equal 2 represents a D, and N equal 3 an F. The third quantum number that we talked about is a magnetic quantum number, ML, which tells us about the orientation. So ML also depends on L, so ML can take any value from minus L, etc. to 0 to plus L. We also said that we can figure out the number of orbitals in a shell, and the rule that we use is n squared. That's if we want to know how many orbitals are in a shell. Okay? Now, the number of orbitals in a subshell equal to n plus 1. So that's kind of sum up every rule that we learned the last time. Okay? So, now what we're going to do is a couple of eye clickers. Then we're going to get started with another topic. So, let's start with an eye clicker.
This was 2, right?
And it is numeric, guys, so 1, 2, 3, either 1, 2, or 3. And I'm going to stop it at 1.
I know that 3 F's is possible. And I don't think 2D is possible either, so I think that. But I know that I think 5 is possible.
Yeah, really.
We should talk about it.
First half, too.
Or 4F is real.
Okay. So I'm going to stop it right here and check what is. So I have 2 as 64%. 2 is the right answer. So let's see how that happens. So here it's telling me that A to S, I know that this is go with the quantum theory because at the second shell there is an S. So that's right. B equal 2D, I know that D only the first time we see D is in the third shell. And if we look to the quantum numbers, it tells us n equal to L equal to. This is what 2D means. And that doesn't comply with the rules of quantum theory. L can never be equal to n, because this number in here represents n, and D usually is represented by L equal to. This is why this is wrong. It doesn't comply with the quantum rule. 3p, that means n equals 3, L equal 1, and definitely there is a p in the third shell. You can look to it either way. So yes, this exists. 3f, that means n equals 3, L equals 3, because f is represented by L equals 3. L can never be equal L, so no, that does not exist. So till now, B and D does not exist. 4f, that means n equal 4, L equal 3. Yes, that's comply with the rules, quantum rules. 5s, we know that s exists in every shell starting from n equal 1, so that make B and D are the two that cannot exist according to the quantum theory. Okay? Refresh your iClicker, because now you're gonna do A, B, C, D. So hit the refresh button before sending your answer. And I'm gonna stop it at 1:10.
Subshell is n. Subshell. Yep.
Okay. I'm gonna stop it right here and check what you think. So I have 73% for D. D is the right answer. So the question, in other words, what is the maximum number of orbitals in n equal 5? We said that the number of orbitals, the maximum number of orbitals in shell equal 5 equal to n squared. So in this case, n equal 5, 5 squared equal 25 orbitals. Okay, so let's do one more. And this is numeric, so sorry, refresh again. Okay. What shall contain a total of 16 orbitals? So I'm gonna stop it right here and check what you think, guys. And I have 4 as 96%. That's very good. Yes, 4 is the right answer. So the total number of orbitals, 16. We know it's n squared. That means the shell is 16, which implies n equal 4. Okay? Now, what is the maximum number of orbitals that can be identified for n equal 4, n equal 3?
This one says for A. I think it might be 7.
Yeah, it's definitely.
Okay. Wow.
Plus L is plus L
Yeah.
Okay. So I'm going to stop it right here. Check.
That's 3P.
So I have 74% for D. D is the right answer. So what exactly the question is asking about that in the fourth shell. So we have 1, 2, 3, 4. There is L equal 3. What does L equal 3 represent?
This has no effect.
S, P, D, F. So the L equal 3 represents an F
I
subshell.
think it picks
So
a
it's
specific
asking
suborbital.
how many orbitals are
Because there
there
are 3 options.
in an F subshell. We know that the number of subshell equal to L plus 1.
-1, 0.
So 2
So it picks one of 3
times 3
suborbitals.
plus 1, that's equal to 7. In other words, whenever I'm asking you, it can be n whatever, L, as long as it complies with the quantum rules. When I ask you about L equal n equal something, L equal something, what I'm asking about is the number of orbitals in that subshell. Okay? And that's usually confuse some of you because you think, oh, she's asking about the number of orbitals in n equal 4 in the fourth shell. No, I'm not asking about the number of orbitals in the n in the fourth shell. I'm asking about the subshell F that is in shell 4. Okay? So in other words, if I give you n equal to L equal 1, how many subshells are there? How many orbitals are there? It's going to be 3. Why? Because L equal 1 represents a P. P have 3 orbitals. Okay, what about if I say n equal 4, L equal 2? How many orbitals are there in n equal 4, L equal 2? L equal 2 represents a D, and D have 5 orbitals, and so on. Okay, does that make sense? Okay. Yeah, I'm going to stop it also at 10. What type of orbital is designated for n equal 3, L equal 1, ML equal -1? So I have 71% for B. B is the right answer. So n equals 3, that's usually the number before the shell, so that's a 3. N equal 1, that's a P. N equal minus 1, it represents an orientation, whether it is Px, Py, or Pz, and usually we don't represent it when we write that, so it's mainly only, it means it is one of these orbitals. So ML minus 1 in here doesn't have a big effect on how I'm gonna write the subshell, the representation of the subshell. So 3p is the right answer. Okay. How many orbitals have the following set of quantum numbers? Okay. So let's focus on these and check what we used. Okay. I have 53% for B. B is the right answer. But let's see how come B is. So it's n equal 4. That means I'm in the fourth shell. And I have n equal 3. That's an F subshell. And F subshell have 7 orbitals. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And this is the 7th. And I'm talking about ML equal minus 2. How many orbitals have n equal 4? It is the fourth shell. It is an F subshell and it have ML an orientation of minus 2. Only one. Because the other one is minus 1, gonna have ML minus 1, ML equal to 0, ML equal to 1, ML equal to 2, ML equal to 3, and ML equal to minus 6. Okay? So whenever you have the three quantum numbers, N and L and ML, you only have one orbital. So whenever you have the three quantum numbers, if I have the three quantum numbers, that represent one orbital. I'm talking about exactly one orbital when I give you the three set of quantum numbers. Now, in the question before, when I gave you the two quantum numbers, that's I'm talking about the subshell. I'm talking how many orbitals in that subshell are there. Does that make sense? Okay, which of the following I'm gonna stop it at that point. Which of the following set of quantum numbers refer to a 4f orbital?
So it would have L equals Yeah. Yeah. That's what I was thinking. I think those are all.
Okay, I'm gonna stop the clock here and check what key. So I have 1, 3, and 4 as 41%. 1, 3, and 4 are the right answers. 3 of them represent an orbital. Okay, let's see how come. So for F, first of all, n equals 4, that's right. L equals 3, that represents an F. ML equal minus 1, yes. So we're talking about one of the 7, 1, 2, 3, 4, 6, 7. So we're talking about one of those 7 subshells. So that represents n equals 3, that does not represent 4F because it doesn't represent the shell in which this 4F is there. N equal 4, that's definitely L equal 3, that represents the F. ML equal minus 3, it complies with the quantum rule that ML should be any value from minus L to 0 to plus L. So that's right, and it also represents one of these orbitals in that subshell. For n equal 4, L equal 3, and L minus 2, it also represents one of those 4F orbitals. So 1, 3, and 4 are the 3 right here. Okay, so by those I clicked, I went over anything you may see, not only in this class or in the exam, because all that I care about that when you go to another course, which is Chem 112, that you know what you need. So if you know those I-clicker questions and you understand them, that's it. You're good. That's all what I want from you in this chapter. Okay? Now we're gonna go to a little bit new topic, which is talking about those S and P. Now we just learned about the quantum theory, what complies with the rule, what doesn't comply with the rule. Now we're gonna talk about those subshells. So again, those subshells. This is the S orbital, the 2s orbital. And this is how it looks. Again, I have to remind you that sphere that I'm showing right here is the highest probability to find the electron. That doesn't mean that the electron cannot be outside this sphere or somewhere else. It's just all what it's this saying that the highest probability to find the electron is inside this sphere. Now, inside this sphere, which is 2s, there is sometimes places where there is 0 probability to find an electron. Now, these we call the place or the part of the boundary surface, which is this one, or the orbital, that have 0 probability to have the electron there. We call those nodes. There is more than one kind of node. There is spherical nodes, and from the name, they are a sphere, like a spherical around the nucleus. And we have nodal plane. That means it's a plane in which there is 0 probability to have the electron. So we're gonna get started with the spherical node. And for S orbital, there are spherical nodes. Now, some of them don't have, some have. We're gonna talk about these. So this node, a spherical node, this node represents a sphere of 0 probability for finding an electron. So let's start with which orbitals have a spherical node, which does not. Now, this sphere in here, we usually represent it by what we call the dot structure, and the dot structure is mainly the dots. The density of the dots represent whether the probability is high or low to find an electron. So, for example, that in that part where you have a very dense dots, that's telling you there is a very high probability to find the electron there. And that density, that probability decreases as you go away, because in here the dots are less. So mainly those dots, the density of those dots, how intense are those dots, how much of them that are there, it represents a probability. Okay, so we call these dot structure. Now this represents the 1s. This is represent the 1s. For the 1s, as you can see, there is no nodal surface, no spherical node. Sorry. And I summarized all what I'm going to talk about till the end of this lecture in this table in there. So what you need to know at the end of this is, if I show you this dot structure, you have to know whether it belongs to 1s, 2s, 2p, 3d. This is what you need, and whether it have a node or not. Okay? Now, let's look to the 2s. When we look to the dot structure of 2s, we see there is kind of a white area in there. It looks like a circle around the nucleus right there. And this is called a spherical node. In other words, in that area, there is a 0 probability to find an electron. Okay? So, for 2s, there is one spherical node. Now, for 3s, this is the dot structure of 3s. As you can see, there are 2 areas. This is the first one. The second spherical node is right there. It's the white area which represents a zero probability to find electron. So there are 2 spherical nodes. So in other words, the number of spherical nodes depend on n. On which shell are we for the s? And the number of spherical nodes for s is n minus 1. So, for example, for s, which is in shell number 1, 1 minus 1, there is 0 spherical node. For n equal to, for s, which is in shell number 2, 2 minus 1, I have 1 spherical node. For 3s, we have 3 minus 1, we have 2 spherical nodes. So the 4s, how many spherical nodes are you expecting for 4s? 3, and so on. And that applies for s, okay? Now, this is the first part of it, which are the spherical nodes for the s. We're gonna definitely go to the p, to the t as we go. Now, so we talked about all these subshells and shells and p and s. So what I'm gonna do is I'm gonna show you how the probability to find an electron as we go by shells. So this is the nucleus. No. So this is the nucleus. This is 1s. So if I have an electron in 1s, this is the highest probability to find the electron. 2s. This is the 2s. And I'm gonna go to 3s. This is the 3s. If the electron is in the 3s, there is a probability to find it anywhere in here. What is the difference from what you've seen between 1s, 2s, and 3s? Now in this, it doesn't show the spherical node because this is a sphere. So if you cut this sphere, you would see the spherical node in this case. But we're looking from the outside on those 1s, 3s, 2s. So I'm gonna redo that so that you. So what is the difference between 1s, 2s, and 3s? For me, it's only the size. As we're going from 1s to 2s to 3s, the size of the orbital is getting bigger, the subshell is getting bigger and bigger. And that's true. If we go from 1s to 2s, 2s is much more bigger than 1s, 3s is bigger than 2s, and so on. Now, the other thing is sometimes it's hard to see when I say, oh, 1s have only s orbital, while shell 2 have s and p. This is what I mean s and p. Because sometimes some of you may confuse it with the following because I draw it this way. this is n equal 1, n equal 2, and I say S and P, and it's hard for some of you to see, oh, how come S and P are in the second shell? So this is the real kind of, the most realistic part of it. That this is both this P and the S, which is the yellow one, they are in the same shell, but each have its own one. Now we know that for 2P we have 3 orientation because it has 3 ML, 2PX, 2PY, and 2PZ. So this is when I say that a subshell has 3 orbitals and they differ in orientation. This is how it looks. Now if I add a 3s, this is what the 3s. So if there are electrons in all of these shells, this is how it looks like. Okay, does that make sense? Okay, so let's go back. So the size of the orbital increase as n increase, if we're talking about S, the same we're gonna see it in P, in 2P, 3P, 3P is bigger inside than 2P. Now let's look at the p orbitals. So in the p orbital, there is, some of them will have the spherical node that we just saw, which is a sphere around the nucleus. Some other of them, they would have what we call the nodal surface, and it is also known, or you're gonna be asked about it on OWL, as the angular node. So the angular node is the same. We're talking about the same thing as the nodal surface. It's equal to the nodal plane. It has 3 names. All of these mean the same thing. Okay? Now, let's get started with the nodal. So the nodal plane is just a plane that passes through the orbital in which there will be 0 probability to find an electron in this nodal plane, in this plane of the orbital. So let's go to the dot structure of p orbitals. So this is 2p. This is the dot structure of 2p. As you can see in here, there is a nodal plane that passes through the center of the 2p, and we call this nodal plane. So there is 0 probability to find an electron in this one. Now for 3p, so this is 2p. For 3p, this is the dot structure. As you can see, there is one nodal plane, and in addition to that, there is a spherical plane, a spherical node around the nucleus. So 3p has both nodal plane and a spherical node around it. Okay. And now the number of angular nodes, or how to know how many nodal plane you're gonna have, it's equal to L. So in this case, L equal to 1. This is why I have one nodal plane for all p. So if I go to 3p, 4p, 5p, I'm going to have only one nodal plane. Okay? Now for S, we said it has 0 nodal plane, and that makes sense now because the S have L equals 0, so that means it have 0 nodal plane. Okay? Now let's go to D. This is 3D. So as you can see for D, L equal to, that means we have 2 nodal planes. And here the first nodal plane, here's the second nodal plane. The same, this is 3D, this is one of the MLs. This is the second one, the second orbital. This is the third one, the third orbital of D. Okay? This is also the other orbital. As you can see, this is the nodal plane in there. And the only kind of, all of them looks like a clover leaf, except this one, the 2z squared, it looks a little bit different in shape, yet it is a d orbital. So this is a dz squared p orbital. Sometimes, and you're going to see that on OWL, they're going to ask you what is this orbital. Make sure that you know that all of these look alike, which is something like this, except one of them looks a little bit different, and it's a stellate, which have also two nodal planes. Okay? So in summary, let's sum up. So spherical node, the number of spherical nodes depends on the principal quantum number, so, and equal to n minus 1. So for 1s, we have 0 spherical node. For 2s, we have 1. For 3s, it's always n minus 1, 2 spherical node. Now, the number of nodal plane equal to L. Okay? So for S, L equals 0, so we have 0 nodal plane. For L equal 1, we have 1 nodal plane, and so on. And that means that's for P. Okay? Okay. Now definitely, as I said before, you need to know, when you look to the dot structure, you need to kind of figure out which orbital are we talking about in there. Okay, let's start with some eye clickers about it. So this is the fourth. The F usually has 3 nodal planes because L equals 3. I'm not going to go into the details of F because it's a little bit more complicated. So I'm just going to leave it aside. So let's get started with this one. Stop it at 110.
Because A is a p orbital and B is a d orbital.
Okay, I'm actually surprised.
I'm going to stop it right here and check what. And I have 2 and 92%. 2 is the right answer. So the way that you have to look at it, first you look to the first one, it's a spherical, so definitely it's not P, not D, not F. It's definitely an F. You look to it to have 2 spherical nodes. We know that the number of spherical nodes equal n minus 1. I have 2, so n equal 3. Or you can just figure out, oh, okay, when I see two circles around this, that means it's a 3s. So that's a 3s. That's a 1s, it has 0 spherical node. That's a 2s, why I have n minus 1 equal to 1, because the number of spherical node equal to 1, so n equal to. So that's a 2s, which makes 2 the right answer. Okay, let's do some more. Okay, I'm gonna stop it at 110. Okay. I'm gonna stop it right here and check. Okay. I have 83% for B, this is the right answer. So what the question is asking, okay, let's say you have A and B, each one have the lowest n of their type. We know that the lowest n, this is a P, and this is clearly a B. We just talked about that, it looks a little bit different. We know that the lowest shell that we can see a P in is 2, and the lowest for a D is 3. So definitely this one have a higher n, the highest n between the two. Okay. Now, one last thing about this chapter is we talked about the first quantum numbers, the second, the third, which is n, l, and m. The last one is the spinning quantum number, and it's mainly, it tells you that each electron, if we have 2 electrons in the same orbital, they're gonna have a different spin. They're gonna be in a different spin, and ms can take a value either plus half or minus half, and those plus half and minus half, all what it's saying is one is spinning opposite to the other. So those are the ms, it's called the spin quantum number. Now, there, if I have n equals 3, l equals 0, ml equals 0, ms equal plus half. There will be no 2 electrons anywhere in the atom that have the same 4 quantum numbers. Because even if it is in the same orbital, even let's say in this one, it is n equals 3, it is ns, and both of them are ml equal to 0, they must have the ms as different, because the 2 electrons in the same orbital, they're gonna be spinning in a different way, opposite to each other. So there will be no electrons out there, or there will be no 4 quantums. The 4 quantum numbers are the same, we're talking about the same electron, okay? There will be no 2 electrons out there that have exactly the same 4 quantum numbers. It can be one of those quantum numbers different, but not the 4 exactly the same. And that's mainly all about chapter 6. We're gonna get started with chapter 7. Make sure that, just a reminder that chapter 5 deadline is the 29th, which is Monday, and that's of chapter 6 is on the 5th of November. Okay? And I'll see you Monday. And have a great weekend.